Hello and welcome. I hope you are having a great day. In this video, we are going to discuss about singular value decomposition. So this is another important concept in machine learning. Okay, but there is a prerequisite for this. You must be aware of eigenvalue decomposition. If not, then watch my video on eigenvalue decomposition. I'll put the link of that video in the description. Okay, let's start. So the agenda is singular value decomposition, and we'll also discuss about low rank approximation, which is just an application or a use case of singular value decomposition. So let's start. So we know from eigenvalue decomposition, so that's why it is important to know eigenvalue decomposition, that if you have a square matrix, if you have a square matrix, then you know how to do a eigenvalue decomposition of that. That is, if you have a square matrix A, which is like n by n dimension, then you can easily break it up. Okay, so this can be written as q lambda q transpose. So this is what is the meaning of this, that q is the matrix which holds all the eigenvectors, orthonormal eigenvectors in the columns of the A matrix. Lambda is all the eigenvalues, and q transpose is just the transpose of this. So remember, this should be orthonormal. Okay, for this format, and this should be a square symmetric matrix, n cross n, and this should be a symmetric matrix too. So this format holds. Okay, a square symmetric matrix. So this is the formula we have seen. So these are the eigenvectors here, which are orthonormal, that is, they are orthogonal by default and for distinct, and then we normalize it by dividing each vector by its length. So this vector is orthonormal, and this is a transpose of that, and this is holding on the diagonal all the eigenvalues, so which gives the scaling. So refer the eigenvalue and eigenvectors video where I discuss eigenvalue decomposition if you don't understand this. So this is the base understanding, that we know a square symmetric matrix can be decomposed like this. But in real life, okay, do we have all the matrices they are square and symmetric? No, right? So we can have a matrix of the format A which can belong to m cross n, right? That is, A is equal to a11 like that till a1m, and this will be amn. This will be a1n, a12, a21. This will be a1n like this, amn, and this will be a m cross n matrix, right? This is how we present. Okay, so that it may, if this is not a square matrix, then the diagonal will not be defined, because it won't fall here, it will be somewhere here or somewhere here. There can be two diagonals. One will be here where amm will be there, and there will be something like ann will be here somewhere. Okay, that will align with this, and somewhere there will be a1 which will align with this. So there will be two diagonals, so that's why the diagonal is not defined. But a square matrix will have only one diagonal, right? That's why we discuss about, that's why all the eigenvalues can be placed around the diagonal, but this will not have a diagonal. So this is a problem. So what to do? But all the matrices in real world may not be square. So is there some way that we can convert this not square matrix or a rectangular matrix into a square matrix? Okay, there is a way. We have studied that during our principal component analysis video. I'll put the link of that also in the description. Say for example, there is a matrix A, then its covariance matrix A transpose A. This will become a symmetric matrix, right? What will be the dimension? If this is m cross n, then what will be A transpose? This A is, okay, this is your covariance matrix, sigma. This is not A. So this is given by sigma, okay, generally. So this is a covariance matrix. So A transpose dimension will be, if this is m cross n, then this will be n cross m, and A is m cross n. So what will be the dimensions of this sigma matrix? This will become n cross n. Yeah, the covariance matrix. So it's become n cross n. N cross n, because it's n cross n, the inner dimensions match and the outer dimension will go. Okay. Similarly, so what about A transpose? This will also become a symmetric matrix. Okay, square symmetric. How? A is, what will be the dimension of this? What will it belong to? So this is m cross n, and this will be A transpose. This will be n cross m. So the inner dimensions match, and this will finally be belong to R of m cross n. This is belonging to R of m cross n. So now this matrix has been converted into a square symmetric matrix, and now we can use this to use our eigenvalue decomposition to form something to convert this rectangular matrix into this decomposed form. And why did we do eigenvalue decomposition? Everything is there because we get a diagonal matrix here. So this is a diagonalized matrix. And lambda is all the eigenvalues put across the diagonal, rest is 0. So after doing these, so this is the hack we are doing, and we can rearrange all these terms to convert this A into a decomposed matrix, which is called singular value decomposition in this case. Why singular value? We'll come to that in some time. Okay, so this A is now represented. I'll give you the exact term. So this A is represented as A is equal to U sigma V transpose. So this is your singular value decomposition formula, or called singular value decomposition. Okay, it's called SVD. SVD, and eigenvalue decomposition is called EVD. So I'll take the short names: SVD, singular value decomposition; EVD, eigenvalue decomposition. So this is there. So what are these things? So your U is nothing but the set of all the orthonormal vectors. So as it was the case for Q, right? So similarly, these are all this is a set of orthonormal, means all the orthogonal vectors. Anyways, for distinct values, the vectors, the eigenvectors will be orthogonal to each other, but we have to normalize them by dividing by their length. So that's how they will become orthonormal, unit length. That's what it means. So set of orthonormal vectors of which vector? Of A transpose. So this is your A. So this is your A. So A transpose. This will belong to which dimension? This will belong to R of m cross m, a square symmetric matrix. Similarly, this is your U. Let me write a clean U. And what will be V? So V will be set of orthonormal vectors of A transpose A. That's what we started with. This will belong to R of n cross n. This is n cross n dimension. This R means this m cross n, n cross n. These are the dimensions that we got. So this is an n cross n matrix that we got finally. Okay. And what is your sigma? Sigma is nothing but this is as similar to this, right? So we will have a lambda, all the eigenvalues. So this is the eigenvalues. This is a rectangular diagonal matrix, and whose diagonal values are, so this is a rectangular matrix. So one of the diagonals. Okay, so generally we have, so whose diagonal values are, so one of the diagonals across the shorter diagonal, which is m, across the shorter dimension. So along that we will have whose diagonal values are called singular values. And why singular values are called singular values? So these are nothing but, okay, these are nothing but, so So you will have this matrix, right? A transpose A. So this is your covariance matrix of A and A transpose. So we get the eigenvalues of this matrix. Compute the eigenvalues of this matrix, and so since A, this is also the form of A, say U transpose U is equal to U square. So A transpose A will be kind of A square, right? So the eigenvalues will also be squared. So finally the eigenvalues what we get will be squared. So instead of taking that, even in eigenvalue decomposition, we saw that that will give me the variance. The variance is nothing but a square unit, right? So if we take the square root of all these eigenvalues, okay, if I take square root of all these eigenvalues, whatever we have, eigenvalues of A transpose A, then, or either of them, both will be same. Okay, the common values will only come. So this will be your, these are represented as sigma. Okay, so this is your, so it's variance, right? This is sigma square, so this will be your sigma. So all the square root of the square root of the eigenvalues of A transpose A or A transpose, these are the entries of this sigma. So what will be my sigma like? So my sigma will be like, for example, my sigma, this is equivalent to the lambda, that will look like something like this. So there will be sigma 1 1, sigma 2 2, like this till sigma r r, and there will be something like 0, some padding 0 will be added. Why is it so? Why is it a rectangular matrix? So let's understand that. Okay, and there is a condition. So we'll arrange it in such a way that they are in decreasing order. So sigma 1 1 is greater than or equal to sigma 2 2 is greater than sigma 3 3, or let me put it, is greater than or equal to sigma r r. And what is r here? R is nothing but rank of the matrix. You remember rank of the matrix? It is nothing but number of independent, linearly independent vectors of the matrix. So if a matrix, if you consider, if this is the matrix here, so all these columns can be considered, or all the rows can be considered as individual vectors. So the number of linearly independent vectors in this matrix, that is the rank of this matrix. And when is the vector not independent? When two vectors are not independent, if one of vector can be presented as a linear combination of other vectors. Say for example, a simpler thing is like, if this is a11 and these are alpha times this second row. So the first row is say v1, this is alpha times v1. So this is just a scaled vector. This is not bringing any new information. So these two now vectors are dependent vectors. So now I have n minus 1. So if this is a n cross n matrix, then I have n minus 1 because two vectors are linearly dependent. One can be expressed as a linear combination of other. So the rank is reduced now. So the number of linearly dependent rows or columns, whichever, okay, is less. So that is your rank of the matrix. That is equal to number of, this is just a revision. We have covered this in detail in my matrix video. Linearly independent vectors in a vectors is rows or columns. Okay, the rows or columns. So that is your rank. So all the linearly independent, only those will come feature here. Okay, and that will become my rank. So why is this? So let's see the dimensions. So this is A. Okay, this is your A is equal to U sigma V transpose. So U is AA transpose, right? So this will be A is M cross N, assuming this is M cross N. So AA transpose is N cross N. So U will become M cross N. So this is your M cross M. Similarly, V is A transpose A. And this will become so this is your, it will become just opposite, right? So this is N cross M. into m cross n. Inner dimensions match, outside is n, so it will become n cross n. Inner dimensions same, this will become outside, this will become n cross n. This is n cross n. So now we should have some matrix here which will facilitate the multiplication. So this dimension should match this dimension here, it should match the inner dimensions of this matrix should match, so that's why it will be m here, and this should also multiply with this, so this will be n here. Only then we can multiply. So this is m cross m, this is n cross m, so this m should match and this n, so only then finally we will have m cross n matrix, and that's the reason this is a rectangular matrix to make the multiplication happen. This matrix multiplication to happen, but only the rank will be equal to the number of independent vectors. So this will be either whichever is less, m or n, whichever is less we'll have those many. So if this is a m cross n, say for example, say m is less than n, right? And if this is the matrix, so this is a m cross n, and if this is the dimension 1 2 3 like this, and this is 1 2 like this till n, so you will have m cross m till that. So you will have the rank will be, say whatever is r, so you will have sigma 1 1 sigma 2 2 like this till sigma rr, and rest will be whatever is the rank if it is less than m, so that rank will be here, and rest everything will be padded as 0 to make it a m cross n matrix, so that this multiplication can happen. Okay, if the rank is equal to sigma mm, then this will be at till sigma mm, and rest we will make it as 0 to make this multiplication happen. I hope this is clear why this is a rectangular matrix. Okay, if this is clear, then let's see that what are the properties. There are some properties that you should know of this this singular. Why are this called singular values? So this is called singular value. These entries of this are called singular values. Okay, let's see the property, then we will discuss why it is called singular value. So let's see some properties. I have told you already, but quickly. So they are the square root of the eigenvalues of A transpose A, and in case of A transpose, both will be same, but you can check that. So we'll take only the positive square roots. So these are square roots, so these are only positive values because we have to show the scaling factor. It should be equal to like lambda. Okay, so it will only be, so these are like properties of singular values. So these should only be positive, so only the positive values will take. So either if we get two values, right, positive, negative, when we take a square root, so we'll take only the positive because we want only the scaling factor, how much it is getting scaled in certain direction. So that's a utility. Second thing is that it is arranged, when we are arranging it in, right, we are arranging it in descending order, descending or non-decreasing. Even if it's equal, then let it be non-decreasing order. That is, sigma 1 1 is greater than equal to sigma 2 2 is greater than equal to sigma rr, where r is rank of matrix. Okay, rank of the matrix A. Okay, that will be the rank of matrix. And now where is this singular word coming from? So eigenvalues, it was like eigen values were coming. So singular is coming from the fact of the rank. Okay, so the rank of the matrix, say for example, as I mentioned, if there is a matrix A11, A21, this is A, A12 like this till A1 n, this is 1 2 till n, and then you have AMN, this is m cross n matrix. So this is A21 like this till AM1 is 1 2 till m here. So say for example, this is a m cross n, so the rank of this matrix will be whichever is less. Say for example, if m is less than n, then if all are linearly independent, then the rank should be m. If all are linearly independent, then whatever is the lower, if rows are lower, then it will be That will be the least number of linearly independent vectors here, right? So the rows or columns are vectors, considering all of them, the whichever dimension the vectors are there. So that will be M. Say for example, two rows are linearly dependent. So this second row is nothing but alpha times. Okay, I'll just is alpha a11, alpha a12, like this till alpha a1n. This is just some scalar multiple. So these two, this row is not bringing any new information. So these two are linearly. This can be presented as alpha times a. So this is like alpha times a1 row, whatever is the row. This, if this is vector v1, this is v2, then v2 can be represented as alpha times v1. Means this dimension of this matrix is not bringing any new information. It's just another scaled factor of the vector which is used within this. This means that the matrix, okay, the matrix. So these dimensions, whatever there, so this dimension is collapsed. So if we calculate the determinant of this matrix where you have linearly dependent rows or columns or vectors, so this will be 0. And such a matrix which has linearly dependent rows or columns is called a singular matrix. Implies they have linearly dependent rows or columns. Okay, linearly dependent rows or columns. Then such a matrix is called singular matrix. You can check the matrix video if you don't remember this. Okay, so singular matrix. So because of this reason, there's a dimension that has collapsed, and because this is not bringing any new information, so the actual number of dimensions of this matrix is not m but m minus 1 now. So this is not bringing any new information. This row, complete row, is not bringing. So there's a collapse in the dimension. So now because of this collapse, this cannot be. This change is irreversible. If you multiply it with any vector, the change will be irreversible. So because of this reason, we say that this is a singular matrix, and because of that reason, this is coming as these values are called singular values, because that is related to your rank, and these values will tell us around some. So some of the values will become 0, 0, 0. Some values will be, because for some of the along certain dimensions we will not get some information. So the values of that will become 0. So you may not get all the eigenvalues now. So the eigenvalues will also be dependent on the number of linearly independent vectors. So those eigenvalues corresponding to that linearly dependent vectors will become 0 here, because the rank has reduced. So ideally it should be equal to, rank should be equal to m if it is m cross n, whichever is lesser. But this will be less than that, and because of that, some of these values will be 0, and those values are called like then we start calling them that singular value for that is 0, the singular value of this is 1, the singular value of other one is sigma 1 1, singular value sigma 2 2, and the singular value is 0. And that's the reason, because of the relation to the singular matrix, this is called singular values. They might be 0 and they can be non-zero also. Non-zero means they are linearly independent and they are bringing some new information. I hope that is clear. So all the dimensions may not bring, but some of them will bring. Whichever brings some information, they are linearly independent, and the sigma for that will be non-zero. So, and we say that the singular value is non-zero, greater than 0. Okay, and whichever dimension is linearly dependent, for that the sigma will become 0. So finally there can be 0 or more linearly dependent vectors or rows or columns in this matrix, and for them the singular values will be 0, and from there this word comes. I hope I have done a long explanation. So the relation with singular and why it is called singular value. These are called, all the diagonal entries are called singular values, and this is represented by sigma, and this is a rectangular matrix to make the calculation hold, sorry, for this matrix multiplication. Okay, and let's see this visually. So this is also sometimes singular value decomposition is also sometimes referred to a set of scale factors, which is scaling factors similar to eigenvalues, that are fundamentally linked to the singularity and rank. Singularity and rank are connected. Singularity and rank of the matrix. whether it is collapsing some dimension, then it will become a singular matrix. And then what is the rank? So because it is this decomposition refers to singularity of the matrix and the rank of the matrix, so that's why it is called singular value decomposition. If the matrix is singular, then the rank will be less than the number of dimensions, the lowest number of dimensions. Okay, so let's move. So say for example, let's understand this diagrammatically, what will be the value. So I have an input, say I have okay, how many are there? So this is 1 2 3, this is 1 2 3 4 5. Okay, and this is transformed, so this is your A, is your A, and this will be your, the next will be your U matrix, right? So let me make U 1 2 3 4 5. So this will be 1 2 3 4 5, 1 2 3 4 5. This dimension is 5 cross 3, right? This is 5 cross 3. So A transpose will be 5 cross 3, 3 cross 5. So this will be 5 5. So this is your U vector, and this will be 5 cross 5. Okay, and then you will have the, so let me reduce the size of this because I will not fit it, or let me move it this side so I can fit all the things. I hope this is visible. So this is your U, then my sigma will come. Let's do this this also. So this sigma will be, this should match the dimension, so this should be same as the A matrix, because that's how it will match the dimension. So I'll just copy this and paste it here. So this dimensions will be same. Okay, so this is your sigma, and the dimensions will be same as this, 5 cross 3, 5 rows, 2 3 4 5 rows and 3 columns, 5 rows 3 columns. Okay, and then I'll have the last matrix. Okay, so let me make it this color. This will be 1 2 3 1 2 3. So this will be a 3 cross 3 matrix. 1 2 3 1 2 3. This will be a 3 cross 3 matrix, because now this will hold. So 5 cross 5 multiplied by 5 cross 3, this will give me a 5 cross 3 matrix. Okay, and then I'll multiply this with 3 cross 3, this and this will match. So finally I'll get a 5 cross 3 matrix, which is this, my A, 5 cross 3 matrix. I hope this picture makes sense. So these, all these vectors, so this is your say for example U is equal to A transpose V, this is your V, right? V, this is your V, and let me write. So you should understand A is equal to U sigma V transpose. Your U is A transpose matrix. So this is, so say the eigenvectors of U matrix are all U1 U2 like that. This is your U1 U2 U3 U4 U5. Okay, similarly, okay, so let me color it. These are the matrices. Similarly here you will have this way. So similarly for V matrix, it will be A transpose A, but this is V transpose, so this will be V1 transpose, V2 transpose, V3 transpose, like that. This will be a transpose matrix. So the column matrix, whatever should come as this, they will be transposed like this. They will be converted to row, because by default vectors are row matrices. Sorry, column vectors. by default vectors are represented as column, and in this whatever is the rank of this, right? So there will be let me write it. So this will be sigma 1 1, sigma 2 2, and then this will be like sigma 3 3, because that is the lower dimensions if all the dimensions are there. So 3 is the lower dimension, right? So that will be the rank maximum, that will be 3. The rank of my matrix will be here, rank is equal to 3, because that is my lower dimension. That can be the number of linearly independent vectors. Only I can have 3 linearly independent vectors here. That is my rank. So these will come here, and rest will be all 0 0 0 for padding, so that the multiplication holds. Now I think this should make sense for you. Okay. So if this is clear, so we are just decomposing my vector matrix into 3 matrices just to diagonalize them, and we know what's the benefit of diagonalization, etc. Watch the EVD video. And finally, all the dimensions are matched, and these are your singular values, and we have discussed also why they are called singular. Okay, if this is clear, then let's do the utility. So what is this used for? Why are we doing this? So these are used for your information compression. Okay, so data compression, image compression. Okay, I'll write that. So let's do a question. So this is used for image compression or data compression. For example, you have a satellite that is taking pictures. Okay, so you have a satellite that takes pictures, some remote sensing, okay, of the earth for Google Map, etc. It is taking pictures, and say for example, for each locality, it is the dimensions of the picture are, it is 1000 into 1000 pixels. Okay, that is equal to 10 power 3 into 10 power 3, that is equal to 10 power 6 pixels, right? So that is like kind of 1 megapixel. So 1 megapixel pictures it is taking, and now it wants to send the information to the ground. So generally satellite bandwidth is very costly. Okay, so you want to preserve the bandwidth and send as much less information as possible. So now the task is, how can we reduce the size of the picture so that the information is sent? So can we send, okay, how to compress the picture so that we can send the picture via satellite link. So now after we had this picture, and with this picture matrix was there, whatever this matrix, it will be a matrix, right? 1000 by 1000. So your picture is equal to a matrix which is a 1000 by 1000 matrix. So M is a 1000 by 1000. These are nothing but pixels, right? Pixels. So you have this matrix. So you did a singular value decomposition of this. Okay, you did a, what will we do? So we will perform a SVD of this, and then find out that what are the, so these are all the singular values. So this is all in reducing dimension. So this sends the most information. As I mentioned, this covariance matrix is capturing variance here. Where was the covariance matrix? So we discussed this in the principal component analysis also. The covariance matrix somewhere I did. Okay, so if not, let me quickly tell you. So for example, A transpose A, this is equal to your covariance matrix is here, right? So the covariance, all the diagonal entries. So sigma, this is sigma 1 1, so sigma 1 1 square, sigma 2 2 square, till sigma n square. So the and rest entries will be 0. So not 0. These will be identical, and rest of them will be giving me the covariance of 2 dimensions. Okay, and this will be symmetric because these are same. So this is sending me the variance of the data on this diagonal, and variance is nothing but information. We have discussed this in principal component analysis. So this is the variance in data, gives me the information that this is capturing, and we have arranged all these values in descending order. So my sigma 1 1, this dimension, all the corresponding eigenvectors, they will capture the highest information. So as we go down, the number of information captured by each eigenvalue or each dimension, okay, that will get reduced, or by each feature that is getting reduced. So after doing singular value decomposition, we found that, so this is a 1000 rank matrix, assuming everything is independent. We found that only top 20 ranks are sufficient to send all the information about the picture. All not, most. From that you can make out most of the information about the picture. That is capturing the maximum variance. And variance is nothing but information, how much variability along that dimension. So we found that the top 20 ranks are sufficient to produce a picture, okay, which will, from that we can make out that, okay, what is the picture about. Say for example, if it is a human face, right? So instead of sending all the 1000 ranks after doing singular value decomposition, SVD, we can just from the top 20 ranks we can make out that this is a human face and what human face it is. Okay, so once we have that information, so do I need to send all 1 megapixel information on the downlink? No, right? So what all things we need to send? So we have done, so A is equal to U sigma V transpose. And how do we write it? If we expand it, so we can write it like U1 sigma 1 V1 transpose, all the vectors. Okay, so there will be 1000 such vectors, right? 1000 by 1000. U2 sigma 2 for that, then V2, along which, so these U1 sigma 1 are all, the sigma 1 sigma 2 are all the dimensions for the singular values along which that is maximum. This is arranged in descending order. So like this we can go to the rank of the matrix, like U R sigma R V R transpose, like that. So this is what we are doing. These are eigenvectors, these are the eigenvalues or singular values here, and this is again eigenvector of the A transpose A. So this is here, and we know that all the rank, so this is say 1000, if the rank is 1000 of the matrix, we know that only 20 are sufficient, so no need to send all the information here, right? So A is equal to sum of R rank matrices. So this is one matrix, this is one matrix, this is one matrix, so we are sending all 1000 or whichever, if R is less than 1000, so we are sending all this 1000 matrix information. This will give me a matrix finally. U1 into V transpose will give me a matrix, right? This is one vector, this is one vector. So we are sending here some this A is, we can write as A is equal to sum of R whatever is the rank, right? R matrices of each of rank 1, because they are having some information, each one is rank 1, and we are sending R such matrices. We can write A is A like that, and out of that we know that R is equal to 20 is sufficient to reproduce the image to a convincing level so that we can recognize. So we just need to say the top 20 images downlink. Okay, so what we do, so what is your UI? Say for example, if it is 1000 dimensions, right? So here we have U1 U2 like that, right? So UI, any UI will be 1000 U1 U2 like this till U1000. This is for the image 1000 by 1, and there will be corresponding sigma for that, sigma 1 which will be positive, square root of that, and then we will have the Vi transpose will be a row, so it will be V1 V2 like that for whichever. So this is say for example U1. Okay, so this is say U only one vector, this is V, so V1 V2 like that. Or this is confusing, okay, so the terms are confusing. So this is UI, so let me write UI1 UI2 like that, UI1000. This is like, this is Vi, this is the first dimension of Vi1 Vi2 like this till Vi1000. So this is a row matrix, this is a column matrix, this will be 1 by 1000. This is just one entry, this is a singular value. So you have 1000 by 1 into 1 by 1000. So if you multiply this back, you will get a 1000 by 1000 matrix, right? Of rank 1, of only 1. And if we sum such till R rank, top 20, so we'll get such 1000 by 1000 matrix 20 times. And we can construct the face back from that. So this is 1000. So if I do just ui sigma I vi transpose, right? So just ui sigma is just a, this is just a scalar, it can go this side, this is just a number, so this is equal to sigma I ui vi transpose. This is 1000 into 1 and this is 1 into 1000, so finally this will give me a 1000 into 1000 matrix which has rank 1 information. That's what I'm saying. Okay, so this is clear. So let's move. So how much information is going here? So now if I, instead of sending the complete 1 megapixel information, what if we send only the top 20 singular values which has the highest variance, which is capturing the most information to do the calculation at the receiving end, instead of sending all the 1000 ranks, if I just send the top 20 ranks. So there are, instead of sending these 1000 matrices, if I just send the top 20 matrices, can they recreate the picture at the downlink and it will be convincing? So what will be the information that we are sent? So we'll just send, so the rank is, so we have to send such 20, so rank is 20, that's why I want to send. And for one rank, how much information I'm sending? For each rank, for one rank I'm sending 1000 entries from here plus one entry for the scaling factor or the singular value, and plus 1000 entries for this vector, for this v vector. So I'm sending approximately 2000 pixels of information, 2000 pixels of information. And for sending 20 ranks, such ranks, how many, what will be the total data sent? This will be 20 ranks. This is approximation, right? So 20 into 2000, that is 2 to the 4 into 10 to the power 4, or just 40k pixels. So consider that the actual size was 1000 into 1000, that is 10 to the power 6 pixels, and just 40k pixels are sufficient. So what is the compression that we are doing in the data? The actual data that needs to be sent, but actually how much are we sending? So data compression would be equal to 4 into 10 to the power 4 by 10 to the power 6. So this goes off, this is 2, so this is 4 by 100, that is equal to 1 by 25. So we are compressing the image like 1 to 25 times compressed image we are sending on the downlink, and data, the data is compressed and the image also, okay, and that is enough to reconstruct the image of the downlink. And that is the use of your, and that's the beauty of your singular value decomposition, that the just top 20 features, okay, just the top 20 ranks where the maximum information is there, they are sufficient to recreate the picture. Not all the information needs to be sent. I hope this is clear, and this example makes the utility of singular value decomposition very, very clear. There are others, so I have told you, so literally let me write it for you. So what are the uses? So one thing we said, image compression. Similarly, if images can, then data can be compressed, data compression also. So one of the data compression, okay, so this is we see the application of this now. Just then we can have noise reduction where you can capture the main structure and ignore the smaller, okay, smaller singular values. So all the smaller singular values will have the noise, and the main capture, what is my voice. So for example, if we are recording a video, if I want to do the noise reduction, then I can eliminate or reduce, okay, or remove the not important noise which is having very less variance or which is bringing very less information. If those are removed, then finally we'll have a noise reduction in my speech or audio, okay. And also we can, this is used in recommender systems on online shopping, etc., right? You have recommended, if you have watched this, then you can buy this also, people like you. So if we have, so a big matrix is created where what is the user and what item they have purchased. So their user item matrix is created, and using singular value decomposition, I can decompose this and find out that what certain user is is most likely to buy, because it will capture all the variance information for similar kinds of user and similar kinds of items. So using SVD, I can decompose it, and then it will work for recommender systems also. Image compression we have seen, noise reduction I told you, recommender systems I told, and now let's see data compression. So I'll give you an example, and that's the second topic of this day, that is application of SVD. Another application, we saw one example of data of image compression and how data compression works, and that is also very famous nowadays. I'll discuss that also. So we are talking about low rank approximation. So just all the formula that we have written, we will just write that same thing. We know already what is low rank approximation. What does it mean? Just get the terms. So this is used for data compression. How can we use? So we can again do, so any matrix or process, okay. So we can, this is a process of approximating. So any data can be represented as a matrix. Okay. So it can be represented as a matrix, and then we can, okay, we can approximate the lower ranks from there, and we can get the information. Okay. So only the lower ranks means the top ranks. Sigma 1 is the low. Sigma 1 1, sigma 2 2. These are the low ranks which are capturing the most information, the top information capturing, but their rank is low. That's why the first rank is the lowest rank, right? Second rank is the lowest rank, like that. So instead of going for the higher ranks, you capture you take the singular values of the lower ranks. These are called lower ranks. So if you have this sigma value is equal to sigma 1 1, sigma 2 2 till sigma r, right? Is m cross n. R is the rank of matrix. Rank of matrix. So here sigma 1 1. So this 1 2 like this, these are rank. Okay, these are the ranks of the matrix, right? So R is the highest rank, and this will capture the lowest information, the highest rank, and the lowest rank will capture the most information. That's why it's called low rank approximation. The rank is for the rank of the matrix, which is here in the sigma matrix. Okay, and the lowest rank are capturing the most variance or most information. So just if I do then approximation on the lower ranks which are sufficient to reproduce my data, then I can use a data compression. I can use this singular value decomposition for data compression, and let's see how. So I hope you get the term correctly now. Why it is called low rank approximation? Rank is the rank of this matrix. Because of that, I get these are singular values, and these singular values are arranged in descending order by design. That's how we have designed that sigma 1 1 is greater than equal to sigma 2 2 is greater than equal to sigma 3 3 is greater than equal to, like that, sigma r. So the lower the rank, the highest the information it is capturing. So that's why this low rank, and we can approximate. I can just choose not all the ranks but the top ranks from here. It can also be called top rank approximation, but low rank approximation, the name has been taken. Okay, and then that can be used for approximating any data that can be presented as a matrix. I hope that makes sense. If that is clear, then let's redo these things and let me give you some terms. So A is represented any matrix. So this is a matrix, can be represented A sigma. Use sigma V transpose. U has the eigenvectors, orthonormal eigenvectors of A transpose, and this is A transpose A. Then you can also write it as, so this can also be written as sigma over I equal to 1 to R, all the ranks. Okay, and I can write sigma I can take out the, as you saw in the image compression also, and then I can write UI and VI transpose. You saw in the this also here, right? I can take out the sigma here and then multiply this. So this was the reason. Okay, so you can similarly do for all R ranks. Okay, here the same image. Where is this? Okay, this one. Let me put it here so that you remember. Let it be. make it big. So this is your matrix. So this is your data matrix. This is your data, okay, in terms of matrix, and then it has been decomposed like this, and these are your ranks. And if I just choose the top ranks from here, okay, and do a summation, you, as I mentioned here, right, if you saw this is nothing but a summation of R matrices of rank 1. Each one has rank 1, rank 1, rank 1, and we summed up R such matrices of same size, 1000 by 1000 size. Similarly, that's what it is saying in the formula. This is also got some name based on some scientist name. This is called Eckart-Young theorem. So just refer that too. I'll just write it somewhere so that you remember. So just refer Eckart-Young theorem. Okay. So this is there. So now instead of, so UI is the ith column, okay, and Vi is the, these are the all the I where it says, so ith column of the vector of the U matrix, and this Vi is the ith column of the here. These are 3, right? So this can be the ith one from here. Okay. So the singular values are ordered from largest to smallest, and the first term captures the vast majority of information. So this can be, if I have to do approximation, so instead of sending all R, which is very, very large, so if I have to send only the K, I know that the top K are sufficient, which is less than R. So I can just send the top K information, and now this approximation, the approximate data. So this is approximated. Approximate data can be written as summation over I is equal to 1 to K, and this can be alpha I UI VI transpose, and it will be a good approximation of the data. Instead of sending all the R ranks, I can just say the top K ranks, which capture the majority of information, and because of this singular values which are arranged in descending order, I will get all the required information, and that will be a very good approximation of my data. Okay, and then your AK, so if it is a reduced dimension now, so AK is having only it is not having the complete dimension. So if you see from the dimensionality perspective, then AK is equal to U sigma V transpose. What will be the dimensions for this? It will not get all the information. This will be M into K. Should R is the rank, so even less than that. So N is there, whatever is the rank, right? So even less than that we are sending. So U should be corresponding to that. So this will be M into K, and this will be my K into K, and this will be K into M. Okay. If this is still an approximation of this, then this will be like this. Okay. So this is the approximate Mn. So Mk, Kk, and Kn. So I'm not sending all the information. This will give me an approximate information with just K ranks. This is the approximation of the data with K ranks. So I'm just sending K information here, not all the information. So instead of sending M cross M, I'm just sending a K which is less than. Same thing here, and finally you will get M cross M. I hope this makes sense. And what is the use for this? So data compression, and very famous, you must have heard nowadays, you must be listening. So there's a method in supervised fine tuning, SFT. So when we have a model and we want to do a supervised fine tuning for that, we use something called LoRa, which is low rank adaptation. Supervised fine tuning, where we do low rank adaptations. This is nothing but an application of low rank approximation. These low rank adaptations are application of low rank adaptations, approximations. Okay, so the A is same, but this is low rank adaptation, which is used for supervised fine tuning, and this is based on low rank approximation, where the top weights of the pre-trained model, they are kept fixed, and the lower matrices, they are trained. Okay, the matrices with lower rank, they are trained. Okay, so this is what is the application. So that is with the content. Let's do a quick revision what we have understood quickly. So this is about singular value decomposition. So we understood why it is required. So all the matrices, so we have eigenvalue decomposition, which we know already, which is for a square matrix, and we do this transpose form for a square symmetric matrix. But all the matrices in real world may not be square symmetric. We will have a rectangular matrix. So how do we deal with that? So for that we use the same trick, that what if I can convert this square symmetric this rectangular matrix into square symmetric matrix. So we did A transpose A, which is it will become a square symmetric matrix, and similarly A transpose will be a square symmetric matrix. And now this can be used to convert this A into a similar to eigenvalue decomposition. I can diagonalize it, and the features will be same as a eigenvalue decomposition. So this is your decomposed form of singular value decomposition, where U is the orthonormal vector, which are normalized vectors of your A transpose. Sigma or V is the normalized orthonormal vector of A transpose A, and sigma holds, this is a rectangular matrix whose diagonal values are the singular values. Singular values are the values which give me the highest variance, and these values are the square root of the eigenvalues of the ATA or A transpose. A transpose A or A transpose, whichever, both will be same, because this will be square of that. Even U transpose U is equal to U square. Similarly, these are kind of square. Okay, and this is also the covariance matrix, which captures the highest variance around its diagonal after the decomposition. Okay, so that's why this captures the highest information on these diagonal elements, and rest are 0. And these are arranged such a way that sigma 11 is greater than sigma 22 till rank of the matrix. And because of the rank, and if the rank is less than the dimension of the matrix, then that matrix is called singular. And since singular value decomposition captures all the information about the singularity of the matrix and the rank, that's why it's called singular value decomposition. And then we saw properties that all are positive, they're arranged in descending order. And then we saw a pictorial representation, that how are these vectors making it back to A. And then finally we saw and solved a problem where we had to send a 1 megapixel image downlink on the satellite, where bandwidth is costly, so we wanted to compress the information sent by the image downlink. So instead of sending the complete picture, we did a singular value decomposition, and we found that top 20 ranks are sufficient to send the picture such that it can be reproduced consistently on the downlink. Then after that we did the calculation and found that for sending just the top 20 ranks, instead of 1 megapixel, just 40k pixels are sufficient, and that gave us an image compression ratio of 1:25, which it was compressed by 25 times, and that saved our bandwidth. And that's the main use case of singular value decomposition. We can have the top ranks, okay, the lower ranks which have the most information, and that can be used. And that is the uses of that: image compression, data compression, noise reduction, and recommender systems. We discussed that, and then we saw one of the applications, that is low rank approximation, where the lower ranks of this sigma are sent as an approximation of the data matrix, and that's what gives you your low rank approximation. And that is used for what is called a technique for supervised fine tuning, which is low rank adaptation. Do not confuse, this is low rank adaptation, where the weights of the pre-trained model are not changed and the lower rank matrices are changed. Okay, so this is a low rank adaptation, and there is a variation of this that is called Q-LoRa. It is quantized low rank adaptation. Okay, so that's all I had to tell you about singular value decomposition and low rank approximation. That's all for this video. Thanks for watching this video. Have a great day ahead, and bye for now.